Welcome back. Today we're going to dive into physiological respiration. What's going on when we're breathing? We're going to dive right into that. So again, as you know, with my previous videos and things, is we dive into anatomy. And that's exactly what we're going to go into. But with anatomy, you have to understand that I'm not an artist and that I'm not an anatomist, even though I know a plentiful amount of anatomy. So this drawing is going to be simplistic, and it's going to help us understand what's going on within the physiological concepts of respiration. So if we have our bronchi and we have our lung, right? That's what it looks like. Bronchi, lung, but then from our bronchi we go to the primary, secondary, tertiary bronchi. That the branches off, and eventually we go to the alveolus. The alveolus is a ton of little sacs and balls, but instead of drawing that, because I'd have to draw in like little minuscule dots, I'm just going to draw a really big one like this, just so we understand what is going on. So we have the lung. On the lung, we have this thing called the visceral pleura. Visceral pleura is attached directly to the lung in a manner like so. Right? It's right on there. And then we have the parietal pleura. Right, so this is like the two teenagers trying to snuggle, and then we have the parents, the parietals. They're just on the outside of the door. Right, so parietal pleura, visceral pleura. Some of you might see pleural cavity, but pleural space. Another anatomically correct thing that we have is lung or ribs, right? And we have ribs completely going along the outside of the lung. So that's kind of what's going on anatomically. As it goes on to anatomically, we have muscles. Muscles are what is going to start this whole thing, right? And the lungs are kind of weird because it's a little bit somatic. I mean, it's a little bit autonomic, a little bit somatic. It's kind of weird in that manner, but this is what's going on. So we have our diaphragm. And we have our intercostal muscles, right? There's two types of intercostal muscles, the external and the internal intercostal muscles. The external intercostal muscles are going to do exactly what the diaphragm does. So if the diaphragm relaxes, the external intercostal muscle also relaxes. Vice versa with the intercostal or the internal intercostal muscle. So let's think about a couple things. First thing I want to talk about is elastic recoil, right? So if we take a balloon, I'm going to explain a balloon a lot today, right? So if you've never seen a balloon, I'm very sorry, but we have a balloon. The balloon is elastic, right? It's very squishy. It wants to expand, it wants to contract, but mainly the balloon wants to contract, but it won't contract if it has a pressure within it. So the lung is about the same. So that's called elastic recoil. If you blow up a balloon and then let go, the balloon shrinks as fast as it possibly can, elastic recoil. Our lungs are the same way. Our lungs want to contract, but it doesn't contract because of something called negative pressure. Now, negative pressure, you might not be completely familiar with the term negative pressure, but negative pressure is a vacuum, right? Mainly just a vacuum. So if you think about a vacuum and you took the main chamber of the vacuum usually has a fan on it, and that fan is just to pull air out. And as it pulls air out, it creates a negative pressure, and then there's another hole at the bottom that opens up. So because there's a negative pressure here, it could suck things up, because we don't live in a negative pressure environment. We live in 1 atm or 760 torr or 760 millimeters of mercury. And so that's what I'm going to draw right here. So this represents, all the way up to your mouth, and this is what you're breathing in the atmosphere. That's what this represents. And so that is 760 millimeters of mercury. But you're like, why did you explain the vacuum thing? That's a very good question. It's because of the parietal pleura, the pleural space, parietal pleura. Within the pleural space, we have -4 millimeters of mercury pressure. And negative pressure represents a vacuum. And because of that, so I did draw this pretty separated. They're close, right? And there's fluid in between them, but they're close. And so that negative pressure keeps it tight and keeps it sucked. And as it's sucked, then we could have inflation occur. And so that force is undermining all the other forces. And so what actually happens with the diaphragm contracts. As the diaphragm contracts, it becomes like this. Obviously, as the diaphragm is like this, we could see that there's more space for the lung to happen. So as there's more space with the lung will begin to expand because the external intercostal muscles are also relaxing, causing the whole cavity to expand. As the whole cavity expands, we could have everything expand. And there's something that I haven't explained yet, but is very important. And there's these proteins that go from the alveoli to the edge of the lung or the visceral pleura. And there's a reason why I drew them squiggly. I drew them squiggly because, as you might be able to kind of comprehend a little bit, as the visceral pleura begins to expand, it pulls on those proteins. These proteins get pulled on, and then they become taut. As it becomes taut, then it pulls on the alveolus. The alveolus becomes bigger. As the alveolus becomes bigger, the pressure within the alveolus decreases. This becomes a -2 pressure. What happens? Air gets sucked into the alveolus. And this is where gas exchange happens, all within the alveolus. So that's why we want a negative pressure within the alveolus so that we can have gas exchange occur and that we can get oxygen throughout our whole body. And that's what I'm going to explain today. But I just needed you to understand what's going on anatomically for it to happen. And while I have this up, I want to just explain something of clinical importance. And that is pneumothorax. Pneumothorax is a collapsed lung. And usually what happens with a pneumothorax is an accident can occur. That accident can be quite wide. There's a spectrum of accidents that could actually cause this to happen. But it doesn't necessarily happen naturally. There's an external force that would have to happen. There's obviously some things that maybe could happen that could cause the pneumothorax, but mainly there's an external factor that causes the pneumothorax. And that external factor is is that something punctures the pleural space, right? Now there's a punctured thing there again. It was a negative pressure. So what happens to a negative pressure when you create a hole in it? Air gets sucked in. And so now it is exposed to the atmosphere. That atmospheric pressure is just going to want to go in and inflate it. And so actually what happens is as the pleural space increases in pressure, the lung collapses. So with all the visceral pleura and all this stuff, it collapses and shrinks right into the alveolus. The alveolus collapses as well. Very, very detrimental because gas exchange cannot happen. Luckily, we do have 2 lungs. I didn't draw the other one because it's the same, but luckily we do have 2 lungs, so we could have some sort of gas exchange happening. But this could happen from a various spectrum of things, like someone could go into an accident, the rib can crack, kind of go in and puncture that lung, and that could happen. Or a stick or something else could puncture it, lead to devastating causes of a collapsed lung. And so therefore, when we fix a collapsed lung, all we really do is kind of try to seal this off, and then usually we stick a needle in the back, in between the ribs, and then just suck out air and stuff, so then we could restore that negative pressure. As the negative pressure gets restored, sometimes we could pump some air into that. We could have a person on a respirator. This will increase, and then we could restore we could restore respiration and gas exchange. So now I want to explain a couple things with gas exchange in general. I'll explain how. So we explained just now how the lungs, how we inhale, but now I want to explain how we exhale. Okay, so now that I've explained how to inhale, let's explain how to exhale. So I'm going to draw a more simple stratification of what I just drew. So let's just have the alveolus, or alveoli, whatever you want to say. And this alveoli, because again, we have the elastic recoil, but there's something that needs to initiate that elastic recoil. It can't just happen because of that negative pressure. So we have water within the alveoli. And this water is very important. And so I need you to understand the alveoli are actually super, super small. They're not this size. I hope you know they're not this size. They're very small. So these water molecules are actually very close together. And if you know anything about chemistry or water molecules or hydrogen bonding, these water molecules want to go together. So if we have water molecules like this, H2O, this is hydrogen bonding. They want to attract together, right? That's just how water works. So there is a force of attraction between the two. And if that force was left alone solely, then the alveolus would contract. But it would probably stay contracted unless we had a stronger force pulling on it. But luckily, we have these things called pneumocytes. Pneumocytes kind of rely like this. They just kind of chill right there. So I'm going to draw a bigger one like this. I'm just trying to see if you could see this because the marker is kind of dead. We have here a head, and this head is hydrophilic, and this tail is hydrophobic. And this pneumocyte, the main reason for this pneumocyte, like obviously, yeah, we have this hydrophobic tail, and the hydrophobic tail kind of pushes it all away, but it produces surfactant. And surfactant increases elastance. And elastance we could draw in an equation called Laplace's law, right? And E equals the change in pressure over the change in volume. That's Laplace's law. So surfactant increases elastance. And that's what's going on here with the pneumocyte. Another important information to understand with a pneumocyte is that it has a cortisol receptor on it. I'll draw that in green. It has a cortisol receptor on it. You might be like, okay, that's kind of weird because cortisol is stress hormone. Correct. But this is mainly due for fetal development. Fetal development has an important role in surfactant. So as the baby is within the womb, around 30 to 32 weeks, the mother might notice that her baby is significantly more active than it used to be. And the reason why it's more active is, I don't know, is beyond me, but it becomes more active and cortisol begins to release. And this cortisol attaches to this cortisol receptor on the pneumocyte, and the pneumocyte then releases surfactant. The whole development of the fetus, the baby doesn't really have surfactant because it doesn't need to breathe, because all the oxygen that it gets is from the mother, so it doesn't need to breathe. But 32 weeks is getting there, right? It's time to come out, and so the baby's getting ready to come out, so it needs surfactant when it comes out to the world so it could breathe, and so we could have gas exchange occur. So 32 weeks, baby becomes significantly more active, cortisol happens, right? Now surfactant's cost. And so that is very important to understand. If there's a baby that is premature, sometimes that surfactant's not there. Or sometimes doctors can do several different tests with the mother and could understand if that baby maybe doesn't have surfactant yet, and they could actually induce cortisol so that things could happen. Cortisol actually, I think, comes from the placenta. Very important stuff. But you could dive a little bit deep into that. I just want to kind of brush over that a little bit. Now, with Laplace's law, I want to talk about a pressure volume graph. I'm sorry, but most of my videos I've had graphs. So if you hate graphs, I don't know. Learn to like them or move on. But I'm going to draw another graph. Because we have a volume pressure graph. Right, max relatively dependent on the person, but max inspiration or intake of the lungs is 4 liters of volume. Then we have -5 to -20 milliliters of mercury pressure, right? Again, that pleural space pressure. So when we inhale, that pressure gets lower. And so we kind of see this very interesting curve within the graph. Within inspiration, I should actually say, but this is what it kind of looks like. So this is a cycle. That's why it's a circle, or it has a loop. It kind of looks like a racetrack. But you might be able to notice some things. You might be able to understand that here, volume is increasing but slightly, but pressure is significantly increasing or decreasing. But here, volume is significantly increasing, but pressure, there's not much change in pressure. And then again, pressure, but less volume. So you're like, okay, Jackson, what's going on? Okay, I need you to remember Laplace's law with elastance. So again, I told you I was going to use that analogy of the balloon several times. But if we took a balloon fresh out of the bag and we started blowing up, it becomes pretty hard to start blowing it up right out of the bag, right? A lot of people actually like to stretch it out a little bit or do a couple things or blow it up a little bit and then take a rest and then blow it up again. But that's because of elastance. It's because that balloon has never been stretched before. And so it needs to stretch at some point. So that's kind of the same with our lungs. Obviously our lungs have stretched before, but the lungs are a little bit thicker and more cool than a balloon. But we have here, it takes a lot of pressure to start inspiring with the lungs, right? Even though the volume doesn't change, and then it hits a certain point, like a threshold point almost, in which the volume significantly increases and the pressure doesn't do anything, and then it goes again. So you might ask, why does this happen again? But it's the same thing with the balloon. If you're blowing a balloon, eventually you get to a point where it's just super hard to the balloon, or else it pops. But if you didn't get to that point where it pops, if you knew almost exactly where that point was, then it just gets harder because it's reaching maximum volume. And so that's the same thing with happening with our lungs. It's reaching maximum volume, so it just begins to slow down a little bit. So we could actually take the slopes of each of these different sections, and here we could see a decrease in elastance and then an increase in elastance and an increase in elastance here. So that's how it kind of goes with Laplace's law. I also want to explain a certain equation that could slightly go with this, slightly not, but this is called alveolar filtration equation. So if we have pressure of the alveolus in oxygen will equal to this thing called FiO2 times pressure, ATM, or atmospheric pressure, minus pressure, H2O, which pressure H2O is just humidity, level of water within the air, what level of gaseous water, minus pressure carbon dioxide over R. Now that R is a ratio of carbon dioxide per oxygen. And so the closer that gets to 1 can mean a myriad of different things. Like when you're on top of Everest, that's pretty close to 1. And that's what's going on with R. So pH2O is actually usually 50. Usually the amount of people have the same amount of humidity. Our body really tries to maintain that amount of humidity. So usually you could actually just put 50 there. Pressure ATM also changes, but not much. Dependent on, if you're in San Diego, California, or Denver, Colorado, obviously the elevation changes. And then this is also another percentage of what's going on with the oxygen. So this is very important because think about this in a clinical setting. We cannot just, someone comes in, they're like, oh, I have trouble breathing, whatever. You can't just be, okay, I'm just going to stick a needle in you and then take it out and measure it. Like, first of all, you stick a needle, maybe pneumothorax would happen. Second of all, that hurts. Third, it's slightly more invasive. A couple things. But math, you could just be like, okay, I just want to time you a little bit. Breathe in, breathe out. Like, that's super chill. So that's what's going on. That's why we use math instead of like trying to poke them with a needle, test their blood, take them to labs, all that stuff. And actually we have computers and apps that do this now. But now you might be like, okay, Jackson, so when we inspire, what do we do with that stuff that we inspire? You keep talking about gas exchange. What's going on with gas exchange? Good question. That's what I'm going to explain right now. Where exactly is this carbon dioxide coming from? And where exactly does the oxygen go? And how do we exchange these gases? So we have the alveoli, and then we have this kind of thing going on here. And again, anatomically, physiologically, we kind of use red and blue for certain things, and that's exactly what I'm using them for. Right? We have the atrial side and the ventricular side, and then we have like capillaries in between. Now, if I could shade it all in, that would be awesome. I'm not going to do that. So we inspire, right? We breathe in all this gas, right? Our atmosphere is built up of nitrogen, carbon dioxide, and oxygen, and other things. But those are the mainly important ones. And so I'm going to actually just talk about oxygen. So we inspire, we breathe in all that stuff, but let's just talk about oxygen. That's what's important. That's what we want to know. Oxygen comes in here, and then it transfuses to here. And you're like, okay, Jackson, you're skipping a couple steps, bro. Like, I know. So let me explain some physics. I know this isn't a physics channel, but I'm going to explain some physics so you could help understand what's going on. So if we have a beaker or a cup or whatever, and then we attach this beaker cup thing to another tank of oxygen, and this tank of oxygen is like this. It's attached to this tank of oxygen. And in this beaker, we have a plunger. And this plunger is airtight, and I mean airtight. Right? There's no air coming through. And then before we put the plunger on, we have water. And this could be just simple drinking water. But
touchdown end zone! Jeremiah Smith, his second tonight. And now a downfield shot on first down for the end zone. Touchdown! Ohio State strikes first. The freshman Jeremiah Smith downfield and going up making the catch is Smith.
No chance that safety is going to stay with Jeremiah Smith.
He's got it! Jeremiah Smith, game clincher.
this is oxygen gas. And so somehow we're able to get all this gas out, and then we're going to put this pure oxygen gas. So oxygen actually has a specific number that helps it dissolve or diffuse into liquid or something else. And that is 102 millimeters of mercury. As it goes from 102 millimeters of mercury, water will begin to dissolve into the water. Not all the water, not all the oxygen, but some of the oxygen will just begin to go in. And this is exactly how carbonated beverages are working, except it's not with oxygen, it's with carbon dioxide. But it's the same thing. As we push down on this plunger, we increase that pressure, then we can actually we could diffuse these molecules into the water. And so that's what's going on right here, is we have that pressure. There's a significant amount of pressure within the alveolus. And so in the blood, we have these things called red blood cells. And these red blood cells have a hemoglobin molecule in it. We need to understand affinity and how hemoglobin sometimes really, really likes oxygen, right? And so hemoglobin's kind of just like a college-age bachelor. Sometimes that college-age bachelor really wants a girlfriend, and sometimes that college-age bachelor doesn't want a girlfriend at all, right? And it's kind of up and down with it. So this, in the hemoglobin at the top, is called T state. T state is tense state. It's the hemoglobin's tense. He wants a girlfriend, right? He wants it. And so what actually happens is he wants that oxygen. So we need to understand also concentration gradients with the aspect of pressures and things. So there's not much oxygen right here. Oxygen begins to diffuse into the blood, not into the red blood cell, but into the blood. So we have all this oxygen, but waits until it hits 102 millimeters of mercury of pressure. Once it hits then it will enter the red blood cell. And then hemoglobin is like, yes, I get to be with oxygen. So oxygen begins to attract to hemoglobin in the T state. Hemoglobin is in the T state. The 10th state has a high affinity for oxygen. Hemoglobin also has an amino acid on it, and it's a myriad of amino acids, so I'm just going to represent it as amino acid. And that amino acid has carbon dioxide connected to it. That's just for us to know right now. So I'm going to draw another red blood cell, and it's going to go like this, right? Arterial sides go to the target cell. Venous goes back, right? Venous is pumped by the musculovenous pump. Atrial side is pumped by the heart, right? So I could draw the heart and like how it's all going, interconnecting, and from it gets oxygenated and it goes into the heart and gets pumped out, right? That's what's going on. We could have the heart right here that's pumping it all, but let's just understand this. Hemoglobin travels to the target cell. This target cell could be anything. It could be a muscle cell, it could be a hair cell, it could be a skin cell, right? There's so many different things that this cell could be. But today I want to discuss it as a muscle cell. But it literally could be anything. Something that goes through cellular respiration. So this muscle is working around a lot, right? Say you just ran a marathon. This muscle is working out a lot, right? And this muscle needs ATP, it needs oxygen, it needs things that help it to keep going. But as it goes through cellular respiration, it produces carbon dioxide. So this is actually a high concentration of carbon dioxide. So I'm just going to draw carbon dioxide like this. Just high amounts of carbon dioxide. And so the same thing happens. Right here is actually low amounts of carbon dioxide. Carbon dioxide begins to penetrate and go through here, right? And hemoglobin's right here. But hemoglobin is tired after their journey. Their journey might not even have been that long. It could have just been going to the thoracic cavity. Who knows, right? But it's tired, right? And again, it's like that bachelor. Sometimes it wants a girlfriend, sometimes it doesn't. And so now he just wants to be with the boys and he just wants to chill. He is now in our state. He's in a relaxed state. As in the relaxed state, he doesn't want oxygen and oxygen doesn't want him. It's mutual, but they don't want each other because the oxygen's like, okay, you're too relaxed for me. I don't want you. And the hemoglobin doesn't care because he's too relaxed. Oxygen goes in, diffuses in, right? This has a low concentration of oxygen because it's already used it all for cellular respiration and things. Oxygen goes into there, and then we also need to understand that amino acid with the carbon dioxide is there, but the carbon dioxide goes through conformation shift, right? And we've already discussed it in my last video, but if you take water, you take carbon dioxide, and you take carbonic anhydrase, we have bicarbonate and hydrogen ions, right? Carbonic anhydrase, I'm just going to do Ca, carbonic anhydrase, is the one that does it. So 70% of the carbon dioxide that we have within our body is actually in the state of bicarbonate. So then this cell is actually high concentration of carbon dioxide. We'll go to the top, and as it's a high concentration of carbon dioxide, it begins to diffuse again. And this carbon dioxide can release, go within the alveolus, and the alveolus exhales. And so there's always blood moving around, right? And so this might not be happening with one respiratory rate, right? But there's always red blood cells that have carbon dioxide. You're always releasing carbon dioxide because of those cells. And so this is what's happening mainly with the whole cycle of carbon dioxide. This is how we're getting carbon dioxide. This is what's going on. So there's another graph. I want to explain that'll help us understand kind of like a threshold period or not of the hemoglobin. So we have an X and a Y axis. And the X and Y axis is actually built up of just pressure and saturation. Right, so 100% saturated at top. Sorry, I didn't show that earlier. 100% saturation is on top, and then we have like the resting cell, or the PaO2, or the atrial pressure of oxygen, right? So the pressure of oxygen within the atria. Right, remember that cycle that I just drew. So we actually have, I'm just going to draw it in red so it stands out a little bit. It doesn't need blood or whatever. We actually have it go like this. And so it's kind of an S curve. This is at 100. I know the scale's a little off. But the question is, what's going on right here? And the answer is T state. And that's actually happening at 40. We do that, and then we just say T state. 10th state happens, and the hemoglobin saturation increases significantly, right? Because it is necessary for the hemoglobin to want to have the affinity toward oxygen to receive the oxygen. So that's what's happening. Then once it receives that affinity, it just skyrockets. This is probably a little off, actually. It's more like this. Skyrockets and becomes 100% affinity. And remember, it does not move on. The hemoglobin with the red blood cell does not move on until it has 100% saturation of oxygen. And so that's actually what's going on. So we can have some shifts within this. We have a shift here, and then we have like a shift like this. So we have red or blue and green shifts. Now, this shift, the blue shift, is O2 comes off easy. Like O2 leaves easy. And this is O2 stays hard. Stays on. O2 stays on and it does not leave. And so something we need to understand about the T state and R state is there's something that changes from T state to R state. It doesn't necessarily just change, but there's a molecule that happens. And this molecule is a pretty cool molecule. Let me explain it. Okay, so we have 1,3-BBG and 2,3-BBG. So 1,3-BBG is T state signaling. And then mainly the whole point of this is to understand one thing, and that is an enzyme. And let's just do that enzyme in green. The enzyme is what changes the conformation of 1,3-BBG to 2,3-BBG. And that is 1,3-BBG. And that's what it is. And so that's what's going on. It's 1,3-BBG mutase. And so if we want to change from T state to R state, 10th state to relaxed state, we take 1,3-BPG mutase, and it will change 1,3-BPG into 2,3-BPG, or the R state. And so how does 1,3-BPG come in? An increase in temperature, an increase in pressure, an increase in oxygen saturation will help it go from T state to R state. Yeah, I think that is it for now, and I will see you in a little while. See ya.